we're beginning a new section, still in chapter 2, I believe, yeah. And the one that we're going to be doing, camera's kind of moved funny. Let's move it. There we go. What we'll be doing today is looking at a section called bell-shaped data. You see it? And these are the main things that are explained in this section. So we're going to start by looking at how we use our TI-84 calculator to find the mean and standard deviation. You could always get the mean with any calculator, but the standard deviation is much more difficult. And not all the questions in WebAssign give you a salt button, because if there's a salt button, you would just use that, right? You would just let it find it for you. So we need to show you how to do it by hand, well, essentially the calculator. And then we're going to look at this thing called the empirical rule for bell-shaped data. And then we're going to, after that, test for outliers, which we actually know, but it's in here, so I'm bringing it back. And then something new, which is called the standardized Z-score. Actually, they tend to just call them Z-scores. So first one in the list is how to use your calculator to find the mean and standard deviation. And so that's where we're going to go. Now, we have covered this when we went and used it to find 5-figure summaries. And so here it goes. And I'll put it over here. So first thing you're going to do is hit the start button, as you always would. And number 1 for edit. And just hit a lot of delete buttons. So it's exact same instructions as last time until it's clear. And then you put your data in. So let's suppose that I had some data that looked like this. There we go. So you just type the data in, 17, 16, 10, 9, 8, 23, 41, and 17. You don't need them to be order, you just type them in. So once you've got all your data in, you hit start button again. You now move over to calc, just like we did last time, and number 1 variable start. So nothing's different. Can you remember how you get L1? Because you had to press 2 buttons. Can you remember how you get L1, which is what I'm going to be typing in here? Anyone? Okay, you hit second button, number 1, and then you hit enter. And in this case, the mean is called X bar. It's 17.625. And the standard deviation of the sample, which this is, and that's typically the one you're always going to use, is 10.7 to 1 decimal place. And that's it. So anytime you need to find, in fact, question 1, is it question 1? I think it is. I think it's question 1 in this section. That's the first thing you get to do. Calculate mean and standard deviation. So you really do need to have a TI-84. So look into, what would that be? I think it was Monday's. Was it Monday when I showed you last time? Look into Monday's video, because I've given the instructions how you do it. You basically email Cheryl Phillips and tell her you'd like to get a TI-84 for the quarter. She'll give you a loaner, and then you go down to the college and pick it up. That's essentially what it is. Any questions about that? Do you feel you could do that process if I gave you any list of numbers? Now, if you do not have a calculator that can get standard deviation, you may have a calculator that can do it. So have a look at its little manual, you know, little paper manual, and look at standard deviation. And if it says, yep, we do it, and this is the buttons you press, then that's fine. But most scientific calculators aren't really designed for statistics. So you may not have that feature, even though you've got lots of other features. So if you don't have it, you're going to have to get a TI-84 or something similar to it. You don't really want to buy these. It's a lot of money for just a few times in this quarter that you're going to use it. But the few times that you're going to use it is indispensable, right? You can't avoid it. So that guy there, by the way, I should put its name down. It's called the sample deviation. Now there's another guy that occasionally pops up, and it's called variance. And variance is just the standard deviation squared. So if you take, what's this, 10.7, you multiply it by itself, and then say round it off a little bit, that's about 114.5, at least to one decimal place. So if you're asked to get the variance, which isn't that common, but if you are, it's just whatever the standard deviation of the data is squared. Are we good so far? Now, that's step one, or topic one. How to use your TI-84 and to calculate the mean and standard deviation and the variance. Do you want me to do another data set, or are you comfortable that you could do that? You want to see another data set, or you feel comfortable you could do that? Okay, we'll do one more. So let's call this data set class A. And let's suppose I have another class, class B. Who knows, it's an art class or something, right? So we've got kids doing finger painting, and we've got their mums doing something else. In this second set of data, oh, by the way, 1, 2, 3, 4, 5, 6, 7, 8. So this data set had 8 numbers in it. And I want to compare this art class, very small art class, to another one called class B. And this art class has 10 people in it. So it's not the same data size. And the numbers this time are 15, 18, 21, 23. I'll put a 10 there. 1, 2, 3, 4. They don't need to be ordered. The reason I'm putting them in order is for some other reason. 1, 2, 3, 6, 7, 8, 9, 10. So they're there. And we are going to find the mean and the standard deviation. By the way, standard deviation is called SD as well. I like SD on this X because it makes me think standard deviation. So we're going to find the mean and the standard deviation of this data set. So here it goes. Same buttons. Hit start. Number 1, edit. Hit delete till the old data's gone. Type in the new data. So there's a 10, 15, and 18, a 21, 23, another 23, 24, another 24, 25, and a 26. That was it. Then hit start a second time. Move using the cursors over to calc, option 1. And now this time you're going to tell me the answer. What 2 buttons do I press to get L1?
Second and then 1.
There we go, and press enter. And the only numbers we're interested in are the mean, which is 20.9. And the standard deviation in this case is about 5.1. You feel a little bit more comfortable about the process? Right, hit button 1, 2, 3, 4. Same buttons. Only main difference, I guess, is that you type in different amounts of data. I guess that's the only thing I can think of. Right, since I've got 2 classes, let's compare them. This is class A, and its mean was 17, I'll round it off, 17.6. So the average age of people in art class A was 17 and a bit, and the average class in B was 20.9. So based on just these two numbers, wouldn't we say that the second art class, the students were probably on average, right, a bit older, about 3 years older, right? Good, a little bit bigger, a little bit older. Now, standard deviation of class A was 10.7, and the standard deviation of class B was 5.1. Now, the mean is basically the number that tells you the typical person in the class. So in this class, the typical person's around about 17 or 18. In this class, the typical one's around about 20, 21, right? That's the guy in the middle. Standard deviation is a measure of how spread out the data is, right? Are they all pretty much the same, or is it all over the place? Class A, the standard deviation is 10 and a bit. In class B, it's 5 and a bit. So it doesn't mean this class is much more spread out. There's a lot of variation in the ages, and this one, not quite as much. Now, if you look at the raw data, it's a little bit easier in this case because they're in order. Would you agree that these start at 10 and finish at 26? So it's quite a short gap between the biggest and smallest. In this case, wasn't 9 the youngest, and it was all the way up to what, 41. Can you see that's a lot more spread out? So those two numbers are measure of center, as we call it, and measure of spread. So let's move on to the second one of my list here, something called the empirical rule for bell-shaped data. Bell-shaped data is just another name. There's a lot of names for this. Do you know how when you get single hill data, wouldn't we call that symmetric? And wouldn't we also call it bell-shaped? It even has another name, so I might as well tell you that name right now. This data is symmetric. It's bell-shaped. And it's sometimes called normal. I guess normal just means that it's very common. It's a normal kind of data set, right? If you randomly collect a lot of data on a lot of different situations, a fair majority of them end up looking roughly like that, right? So people's ages, people's weights, how much money they make, how old their car is, what they got in their last 20 tests. That's a very common shape. They're calling it bell-shaped for right now, so I guess I'll stick to using that term for a little while. And we are going to look at what's called the empirical rule. So it has been discovered through experience that, let's suppose we collected some data and the mean was 100 and that the standard deviation was 5. Right? Just imagine that's what we got. What the empirical rule says is that right in the middle, where the highest peak is, where the most common score is, that's where the mean lives. Would that seem reasonable? The center of the thing is where the mean would be. So that's X bar. And then they discovered something quite amazing. If you go 1, 2, 3 standard deviations, so the mean add 1 standard deviation takes you to 105. If you add 2 of them, it takes you to 110. And if you add 3 of them, it takes you to 115. And then if you go back the way, 1, 2, 3, you get 95 if you take 1 standard deviation, 90 if you take 2, and 85 if you take 3. So you actually get an idea of how spread out the data is. And that's not all. If you take all the data between here and here, right? So that's the mean plus 1 standard deviation and the mean take away 1 standard deviation. In that range, you get 68% of all the data, right? So if you had 100 numbers, 68 of them would probably be, give or take a few, in that range. If you go to 2 standard deviations, I wish I'd brought this down, but it's too late now. Oh, I can do this. I want some more room. Right, so there's the guy again. You don't need this. This is for me. There's 100. And we've already done 105 to 95. And this chunk here, right, from there to there, has 68% of the data. There's 100 again. There's 95. There's 90. There's 105. And there's 110. If you go from the mean and you take away 2 standard deviations, you get to here. And if you add 2 standard deviations to the mean, you get to here. In that range, from here to here, 95% of all the data is in that range. Now, it doesn't matter if you got, you know, the weights of 2,000 people or the age of 180 people's cars, right? This result holds, give or take a little, right? And to complete this, if you take that guy, and there's the mean again at 100, and you go 1, 2, 3 standard deviations, so that takes you 95, 90, 80, not 85, 100, 500, 115. And 1, 2, 3, you go 95, 90 to 85. So from here to here, which is 3 standard deviations, you get 99.7% of the data. So if you take the mean and you add 3 standard deviations, you get to this number. If you take the mean and you subtract 3 standard deviations, you get this number, and 99.7% of the data is in that range. In other words, what almost everybody will probably be within 3 standard deviations of the mean. This table, or this information, has a name. It's called the empirical. It's a full title. I just call it empirical table, but do they have a better name? Empirical rule. That'll do. This is called the empirical rule for bell-shaped data. I mean, if you think about it, that's quite amazing that as long as your data has roughly this shape, that 1, 2, and 3 standard deviations, you get, well, let's put it in red, you get 68, 95, or 99.7%. In fact, that is also a name that we give to it. I like this name better. It's much weirder, but doesn't it tell you everything you need to know? It's called the 68, 95, 99.7% rule. I like that name better than the empirical rule, because doesn't the empirical rule is just a label? Isn't this weird name tell you everything you need to know? 1 standard deviation away from the mean, 68%. 2 standard deviations, 95%. 3 standard deviations, 99.7%. Now, don't we have a rule for testing outliers? Can you remember what that rule was? You took the mean and you added and subtracted how many standard deviations? 3. Correct. Wait a minute. Isn't it those 2 numbers? So when you're looking for an outlier, you are basically calculating the interval where everything's okay, and anything that's outside this limit, this interval. does it kind of make sense now why they chose 3 standard deviations and not one of the other possible numbers? Because if you're an outlier, aren't you a very rare event? If 99.7% of all the data is in this range, isn't there almost nobody outside that range, right? 0.3% is where the outliers live, right? They're the very extreme big or very extreme in the small side. So if you're wondering where that came from, there you go. So if you know this rule, don't you also know somebody's an outlier? Because 3 standard deviations either side tells you where all the good guys live. Anything outside is an outlier. Any questions about that, or are we good? Right, let's give you an example of how that empirical rule would be asked in a homework question or even a test question. Right, the typical amount of sleep that college students get is bell-shaped. It has a mean of 7.4 hours, and the standard deviation is 1.9 hours. And then they have an A, a B, and a C. And in A, they want to know about, because it's a little bit approximate, about what range the 6 to 8%, 95%, and 99.7%. So what range does about 6 to 8% of the students get sleep, right? So what number to what number? And isn't that basically 1 standard deviation away from the mean? So about 6 to 8% will be the mean plus or minus 1 standard deviation. What does that get me? If you take 7.4 and you subtract 1.9, that'll tell us the small end. And that's 5.5 hours. And if you take 7.4 and you add 1 standard deviation, you get 9.3. So about 6 to 8% of college students get around 5.5 to 9 hours sleep. Right? It's a big chunk of them, right? The big chunk in the middle tend to sleep in that range. Now, if you go to 95% of the data, let's see what that looks like. Well, that's the mean plus or minus 2 standard deviations. So I take 7.4 and I take away 2 of them. So 7.4, the mean, take away 2 times the standard deviation. And that's 3.6. And then you take 7.4 and you add 2 times 1.9 and you get 11.2. So 95% of students get about 3.6 to 11.2. There is something wrong with you if you're getting 3.6 hours of sleep. But maybe this was on one day, right? They just took, what did you do last night kind of thing, right? But even saying that student did not get a lot of sleep. That one was comatose. But you can keep going, because if you want to know what virtually every student would do, it's the mean plus or minus 3 standard deviations. And so 7.4 take away 3 1.9s get me to 1.7. And if you do the other one, it's 13.1. So pretty much somewhere in that range, every single student in your data set fell. Now, if there was a student who said, oh, I slept 14 hours last night, wouldn't that student be an outlier? And if one of them says, I didn't sleep at all last night, so I guess that's 0, wouldn't that person be an outlier? Are we comfortable with the empirical rule? I'm calling it empirical rule because it's easier to say than the 6 to 8, 95, 99.7 rule, right? You comfortable how that rule works? So if you were collecting data on anything, let's suppose you're an astronomer and you were collecting data on how big stars are, right? You've got a way of measuring how big they are. And you would collect thousands upon thousands, probably done by computer, weights of stars, masses of stars. And you would be able to calculate this and this, and we would hope that stars have a rough bell shape. And then couldn't you go looking for outliers? Because very often in science, isn't the exception more interesting than the rest? And so you go looking for anything that is outside the range, because the outliers would be probably more interesting. So far, so good. Right. Let's make up a question for the next example of that same thing. Let's suppose that I collected data on, some massive number, like 20,000 patients, right? So 20,000 self-identified males. And I collected from them their potassium level. I have no idea, I'm making this data up, right? And the mean potassium level for adult males is 32 units. And the standard deviation for adult males is 5. Now I'm going to create the bell shape data for that, and then I'll show you one of the uses that they do with this kind of medical data, but you can imagine it would be real medical data rather than this made up number. Right, so right in the middle goes 32. I'm picking 5 because it's easy for my brain to keep adding 5s to things. And going back the way, it's going to be 1, 2, 3, and this one is what, 27, 22, and finally 12. Okay. Now I'm not going to do the 68, 95 one, although I could. I'm just going to go and cut to the chase and do the last one. So the mean plus or minus 3 standard deviations, right? That would be from here to here. Now, don't we know that that is 99.7% of all potassium levels would be in that range? And so in this case, it would be 32 plus or minus 5. And can you see that's where the numbers come from? So you end up with 12 to 47. Now, if you've ever had blood work done, do you notice that they very often tell you if you're outside the normal range? If you wondered what's the normal range, can you see that would be the normal range? And so if you had a potassium level of 52, wouldn't you be considered a high potassium level? And they'd go and say, well, that's not good. There must be something maybe wrong with you. Of course, if you got a potassium level of 8, wouldn't that be considered exceptionally low? So all that, so if you think about any blood, if you do a bank of tests, don't they always have a range at the right-hand side? This is the normal range that people have. And then they look at your specific number, and if it's okay, they don't say anything. But if it's a bit in the big side, they'll say high, and a bit in the low. Now, you could do that a little bit more sophisticated. Couldn't I say that was extremely high and extremely low? And then couldn't I use the 32, which is the mean, plus or minus the 2 standard deviations? And that would give me the 22 to 42. Now, if you're outside that range, wouldn't you just, you would say, oh, your potassium level is high, right? It's, nothing, that you're going to end up in the hospital with, but we should keep an eye on it. Maybe when you get this potassium level, the doctor's going to be really worried about it, right? That is not good, right? That could be life-threatening, and it could be health-threatening. So you might have high, extremely high, right? So the little bit more degrees of relativeness, right? So you either just have one big one, right? You got a problem, or sometimes they say you're high, and then they have another range for extremely high. Are we good with that? Now, where did they get this data? Well, don't doctors collect data on you every time they do blood work? And very often that data is collected by medical places like UW Medical Department. No personal information is attached to those figures, right? So it's not that they know that this data is yours. So this data is pretty good. People share it a lot. It's not going to infringe on your privacy. And so they get huge, massive sets of data. And that means that they are really, really comfortable or confident about these ranges, right? They know them. It's not like they just got 10 people and they got lucky, right? It's like 10,000 people. So you really can bet your money that that's good data when you get it because of the size, if nothing else. Are we good with the empirical, the 68, 95, 99.7 so far? Now I'm going to use that same data, this empirical row stuff, to calculate some other, a little bit more awkward. So I'm going to make the numbers nice and easy at least to deal with. You heard the IQ scores before? Pretty sure you have. They used to be a lot more important and bigger in the past. Today it's kind of novelty. But the average IQ of an American adult is about 100. And the standard deviation is about 10. So if you get an IQ test, you get an IQ test like 112 or 92 or whatever it is. That's where it comes from. IQs are bell-shaped data. And the typical average American adult, as you'd expect, is there. Now I'm going to create that 1, 2, 3 standard deviations. Take away 1, take away 2, take away 3. And I'll just remind you, 68, 95, 99.7. And you are going to get questions that superficially look impossible. But if you work on it, you can actually get the answer. You're going to get things like this. What percentage of Americans, adults, have an IQ greater than 110? And you're going to say, you can't do that. I can tell you the middle 68, the middle 95, right? And the middle 99.7. Nowhere does it tell me, at least directly, what that is. So let's show you how you could do that. Let's choose some colors. So you're going to have to be with me because this diagram's going to get really messy really quickly. What percentage of people are between 90 and 110? That we know. What percentage of people are within 1 standard deviation of the mean?
68.
Now, would you agree by symmetry that the 68 is both of these added together? Wouldn't that make this guy 34 then and this guy 34? Are you with me so far? Now, we are actually interested in that side, aren't we? So far, so good. We're almost there. Isn't 50% of the data this side and the other 50% of the data is that side? Agreed? If this bit is 34, what's left there?
16.
And you do that by 50, take away 34, 16%. So the question is, what percentage of people have an IQ greater than 110? The answer is 16% of the population. So do you see that we used that table, but we used it in a way you didn't think it was going to be used, right? I mean, we're trying to get as much mileage out of it as possible. Second one, what percentage have an IQ less than 80? So I'll draw my picture again. Take me a little while to do this bit. I guess if you were doing it with pencil, couldn't you just rub it out and use the same one over and over again? But since I'm doing pen, that's not going to work. So there's 90, there's 80, there's 70, there's 110, there's 120, right? There's 130, right? There's our little guy. Now, if you look at 80, it's here, right? And that's what, 2 standard deviations away. So if I go to that, what percentage is in the middle here? What percentage of people have an IQ from 80 to 120?
95.
95. The same argument I gave before, doesn't that split into 2 halves equal? Right, so if you do 95 and you split it into 2, just to make sure I'm not doing it wrong, you get 47.5%. And on this side, you get 47.5%. With me so far? Now, same thing as before, isn't that 50% on this side and the other 50% is on that side? And we are interested in this bit, aren't we? Great. Now, what is that? What percentage is left over?
2.5.
And didn't you do a similar calculation? 50 take away that piece. So the answer would be 50, take away 47.5%, and that leaves you with 2.5%. So roughly 2.5% of the population have an IQ less than 80. And well, we've got 16% and so on. So do you see that you can use this table to answer questions like what percentage are bigger than this number and what percentage are less than that number? But don't the numbers have to be one of these guys? You can't do it for bigger than 103. That ain't going to happen, right? You can't do it for those. But as long as it's one of those ones. So the final one of this one is going to be the ugliest, the hardest, whatever, to do. I'll try to find this. There we go. So I'll draw my picture and then I'll ask the question. Here we go. There's my 100, 110, 120, 130. Technically, it's a little bit after that. Then it goes 90, 80, and 70, right? And for question C, what percentage of adults have an IQ between 90 and 120? That's going to be the hardest of the 3 to do, right? That's how you get bigger than something. That's how you would find percentage less than something. But this one, if I put a little guy here at the start, right? And I put a little guy here at the end, do you notice that it's not equally spaced? It's more on one side and less on the other. You with me so far? So we're going to have to approach this question. Any suggestions? There's a lot of ways of doing this. Is there any suggestions about how you might do it?
Wouldn't it just be adding the 34% on the left side and then 47.5% on the right side?
It would be. Right, if you look at that, I see others nodding. That's a good sign, because when somebody's nodding, they'll say, yeah, that kind of makes sense. But for those who I can't see nodding, which is one reason I like to see videos, because I get feedback that way. Let's show you that slowly. I'm going to only find that piece right now. Well, if you think about it, isn't it the same as this picture, right? 68 and one standard deviation on either side of the mean is 68. So won't that be 34? Are you comfortable about just that little piece there is 34? I think of it as like a cake, right? You're cutting it, this cake, this funny shaped cake, and you want to find out how much you're getting, right? Well, if I get that piece of the cake, aren't I getting 34% of it? That's a big chunk of cake. Now, I now want to get this piece. And once I get this piece, can't I just add them together, like Mark said, and we're finished? Well, you might say, well, how do I get from 100 to 120? So I don't need to rebuild the picture. Isn't 80 to 120 that guy? 95%. And half of 95% is 47.5. And that is what this piece is. And so if you want to get what percentage of IQs are between 90 and 120, don't you add 34 to this guy? So do you see in this last situation, you tackle it a little bit differently. So that's 70, 80, I think it's 81.5%. Do you want to see another one of these guys, or is that enough to get the gist of how this does? We're good? Okay, I like good. So we've already covered that. And the empirical rule, I guess I should put my other name in here, the 68, 95, 99.7 rule, right? That's another name for it. How to test for outliers? Well, you know, 3 standard deviations. If you're in that interval, you're good. If you're bigger. Now, this last guy, we got time? Yeah. How to calculate and use standardized Z-scores. Well, let's give you a story to show you why you need them. You know, John and Mary are twins, right? And John and Mary took a math test, but they were in different classes. He was in class A and he was in class B. And John got 82 in his test and Mary got 71 in her test. And John, because twins are like this, ha ha ha, I'm better than you. I got to 82. I'm better at math. I'm giving her a real hard time. And Mary didn't like that because she didn't think that just talking about the 2 scores was fair. Because she said, oh, your math professor is dead lenient. He gives easy tests and he gives lots of extra credit. The guy I get, nobody ever gets 100%. He says nothing is perfect. You ever had an English professor where you're not allowed to get 100% on an essay because nothing is perfect, right? She get landed with that one, right? And the other one, John, he get landed with that, well, you know, it's kind of in the right area, I'll give you the points, right? Kind of lackadaisical. So she said, that's not fair. So she got some data and she found out that her class, the average was 50 and that the standard deviation was 10. And John's class, the average was 60 and the standard deviation was 15. Now, when you look at the 2 classes, would you agree Mary was in a class where it's a lot harder to get a good score? Look at the average. Would you also agree that Mary was in a class where there wasn't as much variation, right? Compared to that one, right? That's smaller. And so she says, it's harder for me to get 71 in this class than it is for you to get 82 in your class. And so the question is, well, how can you compare data that doesn't, that's not got the same mean and standard deviation. How do you do it? And you do it by getting what's called the standardized z-score. And the formula for it is the data, take away the mean, divided by the standard deviation. And whoever gets the biggest z-score actually was the person who did best. It's harder to get a big z-score. And the thing about z-scores is they take into account the mean and standard deviation, right? So they make it a level playing field. So you're comparing as best you can, like with like. So let's see what John did. John's z-score. Well, he got 82, take away 60, divided by 15. And so 82, here we go, take away 60, divided by 15. And he got, let's just do one decimal place. He got a z-score of 1.5. I mean, he did okay, right? He's better than the average, so it's not like he did badly. Let's see if Mary did better, worse, or about the same. Well, she got 71, take away 50, and divide it by 10. And, isn't it harder for Mary to get the score she got in her class? Her z-score is bigger than the other one. And do you see that's a much fairer way of comparing two dissimilar scores from two different, distributions? It's called the standardized z-score. Off the top of my head, did you know SATs are standardized? Because one year the SAT is a little bit harder than it was last year, so they always standardize it. So you might have got, a certain score, but then they fix it by bringing in what the mean and standard deviation were for that year. Anything that you see the word standardized in, and it's to do with numbers, they've probably done a z-score thing to it, right? They've probably converted into a z-score, and then the number they give you is probably not going to be the z-score, because people would say, I got a 2.1 in that exam. What does that mean, right? But they still do it, and then they reconvert it back to data. So it's a very common thing. We learned some cool stuff today, didn't we? I got some notes. Bye-bye. Make sure you say your last name.